This is the Pearson Edexcel FP1 paper from 2019, this book here. We may as well get straight into it because it's probably going to be quite a long one. This first question, it should be 5 free marks to everyone, right? You draw a table with 5 places because it's 4 intervals, x and y. Start the first and last with these two numbers here, so 0.4 and 2. And then just choose whatever interval length you can to make it go equally from here to here. So 0.6 works, sorry, 0.4 works quite nicely to get us from there smoothly. Then we type in all of these numbers into there, so e to the power 0.4 squared here, and then e to the power and so on. You get all these. And now the informal way of just knowing Simpsons rule. Simpsons rule is really interesting, and I might make a video on it on its own at some point. But the informal and very easy way to get it right in the exam is to do this. It's a third times the interval length, which is 0.4, and then the ends just mean these two values, the first and last. The odds mean the first and the third, and the fifth if it was there, and the sixth, and the evens just mean the second and the fourth, but this is the end points, that doesn't count. And the first one, the end points don't count, so this is the first and the third, this is the second, so that goes there, the first and the third goes there. You substitute all those numbers in, and you get an answer. And that's the 5 marks done for the first question. Second one, also very nice if you know Leibniz. So you say y equals this times this, so call this f of x, call this g of x maybe. And then we just differentiate these 5 times we need to go to. So differentiate this one 5 times, differentiate this one 5 times. It's not too hard, of course we know how to differentiate functions like this. F of differentiated 4 times and 5 times is both 0, so I'll just stop there. This one, of course, sine differentiates to cos, which differentiates to minus sine, which goes to minus cos, which goes back to positive sine again. And then one more time when we get this here. And now all we have to do, I think, is say k or d to the 5y over dx to the 5 is going to be, it's a bit like a binomial expansion, isn't it? It's this first f times the last g, plus 5 choose 1, because we're going up to 5, 5 choose 1 of the first derivative of f, so the second one in your list, times the second last one of g, and then 5 choose 2 of this one times this one, and it's a bit like a binomial, isn't it? You just keep swapping these. Notice I only need to go to here this term, because f4 is 0 and f5 is 0, so they're just going to make all these 0. Of course, you can just substitute all of this in. You can verify that my numbers are good here, I think, and all my letters are as well, I hope, and we'll get this. Of course, we can collate together the causes and the sines to make this, and we can factorize out from here an x and a k cubed, it looks like. So that looks like it's going to be this one, and that leaves behind a minus 60. We can factorize out from here an x squared and a k squared, which is good because that seems to be what I needed to do. Ooh, where's the x squared gone? Oh, sorry, there's no x squared, is there? It's just a k squared, leaving behind, and a 15 I can take out. That's what I was talking about with that 15 there. And we get this, I think, and I think that matches up perfectly, so we get these 3 numbers. And I hope that is the correct answer. Excellent, so some nice easy start, I think, as long as we know what we're doing with those 2 rules there. Third one, so dy by dx is this, show this thing here. So I just decided to do this in the dumbest way possible, and thankfully the dumbest way possible worked. Just keep differentiating this over and over again. So differentiate this to get d2y by dx squared equals 1 minus 2y dy by dx. Of course, this differentiates to 1 with respect to x. This differentiates to 2y, but that's kind of with respect to y, so we just need to shove on a dy by dx in the end. That's how most of us learn, I guess, implicit differentiation. And now just do it again. Differentiate this side for d3y by dx cubed. 1 differentiates to 0. This is a product, right? So we differentiate 2y first, which goes to 2, and then dy by dx. And then leave 2y alone and differentiate this, which differentiates as d2y by dx squared. And then just differentiate again. You can collect these together for dy by dx squared, of course. And again, now just differentiate. So differentiate this. I did a bit of chain rule here, so bring the 2 down to make a minus 4. That goes down to a 1. And then the derivative of the inside the bracket is just d2y by dx squared. And then this is another product, right? So differentiate 2y for just 2, and then times that by dy by dx. Leave this alone. And then differentiate leave this alone and differentiate that for d3y by dx cubed. And I think, is there some collecting together to do here? Not quite. We can just immediately differentiate again. This is a bit annoying because there's so many products going on. Of course, this differentiates as d2y by dx squared. Leave this one alone, so we end up with just 2 of them. Then we leave this one alone. I've kind of removed the 1 because I don't need it anymore. And then differentiate that for this. And then here, a product here, so differentiate this one for this. And leave this one alone, and then leave this one alone and differentiate this one for this. And then finally here, differentiate this for a 2 dy by dx, because of course you've done some implicit stuff there, and leave that one alone. And then lastly, leave this one alone and then differentiate that, and you eventually get this. Stuff here collects together, and it collects together in exactly the way that we want it. This is d2y by dx squared, which is this bit, which also is here, and also, no, those are the two there, so we get minus 6 lots of those, so I think C will end up being minus 6 lots of them. Yep, so C is minus 6. These 3 terms all go together, I believe. Minus 4, minus 2 is minus 8 of them. And then this term is standalone with a minus 2y there. And I think we have all of the answers as required. Hence, find a series solution in ascending powers of x as far as x to the 5 of the differential equation. So I've put all my results down in here. So this is what I found. I've replaced this with all the constants that we know actually are there. And then I've just written down my result for dy by dx, d2y, d3y, d4y, and d5y should also... Oh, sorry, d5y is, of course, this one here. Okay, good. So x equals 0, y equals 1. Just substitute those values into here to find what dy by dx equals when this is the case. So dy by dx equals 0 minus 1 squared is minus 1. And then now you've got these 3 results, substitute those into there to find what d2y equals at this initial point 0. So 1 minus 2 times 1 times minus 1. Right? And you get this. And then just keep going, right? Substitute in all of whichever values are necessary to substitute those in. You should have, as you work your way down, you should have them all as you go down. So this one ends up being here. You can verify my numbers there. This one ends up being all of this. Again, you can pause and verify if you want to. Equals that. And then the next one, finally, you put any relevant numbers you can into here, and you end up getting this, which equals this. And then the series solution ends up looking, I've got all my results written out here, ends up looking like this. So it's like a regular Taylor or Maclaurin series. You've got x squared over 2 factorial, x squared over 3 factorial, and so on. And then you just have all your evaluations tagged on the side here. Not sure why there are 2 pluses there, but whatever. So y0 is 1, this is minus 1, so that's going to be a 1 minus x, and then this is minus 8. Sorry, no, it's not, it's 3. Divided by 2 is just, 2 factorial is just 2, so that's 3 over 2x squared, and so on. And you get, just plug in all the numbers, and you eventually get this. That should definitely say x to the 5, I believe. That's just a typo. That should say x to the 5, of course, otherwise, yeah. So that's this 5 here, should be coming out from there. Good, I think that's the whole question. Lost a mark there for that typo, but that's okay. We have a parabola here. We should know what parabolas look like. They look like this when it's looking like this. So okay, just choose 2 random points. I always just draw the points roughly here and here, just because I know any drawing they ask me to do, I've got plenty of space to do it here. It's talking about tangents here, so we've got tangent to this point, which is looking like this, I think. Tangent to this one looks a bit like that, and they meet at the point minus 28.6, and this looks roughly like it could be minus 28.6, I guess, over here, and then up here, so that's good. Picture sort of makes sense, not that it really matters that much. Okay, so what do we do here? Well, we can first, differentiating this is always the case. What I want to do is I want to find the equations of these lines, right, and set them equal to each other and get this point. But of course, to do that, I'm going to need to find the gradients, which means differentiating. So differential of that, as we saw before, is 2y times dy by dx. Divide by 2y, we get this. And so the gradient of this line is just what happens when I substitute in 4p into there. 8 over 4p is just 2 over p. So the gradient of this line is 2 over p, or just this. And then we can also substitute, this is just y minus y1 equals mx minus x1. So I think that's the equation of this line. I can, of course, do a little bit more sorting out with that. Times by p, divide those two to make a 2. I can also substitute in this point as well, because I also know that. So let's also substitute in that point. And the reason that's going to be helpful after I sort all this out is I'm going to end up with something that looks a bit like this, which is of course very solvable. So I just solve this with p. I actually get 2 answers. I get this or this. And I'll explain what to do with those in a second. Because of course I can now look at this line and just do precisely the same thing. Put in 4q into there and you just get 8 over 4q. Put in that same point because it also goes through that point. That's the intersection there, look. Sort that out a little bit, then shove in this point to get this. Just shoving in the x and the y value. We get this, we get this. It turns out to be, of course, exactly the same quadratic. And all this is saying is that, essentially, one of p is minus 4, or one of p or q is minus 4, and the other one is 7. Now, according to my picture, it would just make more sense for me to call q minus 4. So this would be down at minus 16, and it would make sense for me to call p 7 to make that up at 24. Of course, the squares become positives anyway, which is good, because that means they're both over here, of course, as they have to be on the curve. And we get these 2 coordinates here, so I've just put in those 2 values. I've chosen those, I've put them into there, and I get these 2 values here. And now it's saying show that the area of the triangle PQR is this. So we can just ignore the curve and the tangents now. We can draw a triangle between PQ and R, which will look like this. And now it's just a game of pick your favorite way to find the area of a triangle like this. There's lots of ways to do it. Some of you may watch the video that I uploaded a little while ago on this. The most elementary way, I think, is just to draw a big box around it and say, okay, well, the distance from here to here, the width of the box is minus 28 to 49, which is this. The height is from 28 to minus 16, which is that. And now you can find all these distances. So this one here is from 16 to 49, which is this, which makes this 44. This distance is from 6 to minus 16, which is 22, which also makes this distance 22. And now the area of the triangle is going to be 77 times 44, minus this triangle, minus this triangle, minus this triangle. And we'll end up with our answer that they wanted us to get, which is amazing. There are lots of other ways you could do that. You could have flexed, done a bit of Heron's formula if you wanted to. We all know that's an excellent one to do. Now we've got our t substitution question. Now t substitution comes up every single year on FP1. It's a question that looks very similar to this. It's well worth just having practiced lots of these, and of course knowing that if this is the substitution, the standard t substitution formula, that means sine of x equals this, cos of x equals that, and even tan of x equals that, though it's rare that you need to use this. Though it's also definitely worth knowing where these results come from as well. They come from, I might actually draw it later, they come from a little triangle, angle x over 2, opposite side t, adjacent side 1. Because of course t over 1 is t, and then you work out the hypotenuse. You can do some double angle formulas to get to here. That's where you get it from, but it's well worth just knowing these results because it will save you a lot of time and lots of questions you don't need to derive it in any way at all. So just worth knowing those. Okay, so how do we get this integral done here? So of course we substitute in cos and sine into there. We also need to swap out dx for a dt. So we take this, we do dt by dx, which gives us tan differentiation sec squared, bring the half out. Sec squared is the same as over cos squared, times by cos squared, times by dx. Now, of course, substituting in this whole thing for the dx wouldn't really help us because it's got an x in it. And this is actually where deriving this result comes in handy. I was talking about this triangle x over t with opposite side t, adjacent side 1. So tan of this is t over 1, which is just t. This hypotenuse is, of course, just root of 1 squared plus t squared, but that means cos of x over 2 is 1 over this. And also means cos squared of x over 2 is just this squared, which is 1 over 1 plus t squared. And that's really helpful for me to just put in. Or, of course, when they do t substitution, they often, or most often, ask you to integrate something. You can just remember this result off the top of your head as well. I mean, I wouldn't actually just do that. I would make sure you know how to drive it. Just remember, you can just jump from here to here. I would maybe just memorize that jump, so you don't have to bother writing this out. But anyway, we put this into there. We replace the cos and the sine, as I said we would. And this looks now something that might be doable. This 1 plus t squared cancels with these two, so we just end up with this. And there's a couple of different ways to go from here, and I will do this in a couple of different ways. Of course, you can divide everything by 2 first if you want to, and just write this in the normal quadratic order. And what I decided to do, because I'm stupid, is look at the formula book and look for what integrates to log of something over something. And I found kind of this result here. So I wanted, essentially I was trying to get this result so that I could just integrate to make it look like this. This ends up not being the easiest thing to do. I'll show you both methods, but I'll do this one first. So okay, the aim is to get this looking like this. So let's do that. Let's complete the square. So factorize out of 2 to get you this, and then we can sort of complete the square on this bit in here. So halve that for 3 over 4, take away this squared, which is 9 over 16, multiply the 2 out and add the 2 on the end. 2 minuses make a plus, of course. Add the 2 on the end, we get this. I've also, because that's a minus, I've just put it second and put the positive thing first. This is, of course, 16 over 8, which adds to make 25 over 8, and then I factorize out a half, of course, yeah. So basically brought a 2 out of both these to give me this, and just missing the 2 here. So 2 times this would be that, and then 2 times this would be that. And now this is looking good, because this is something squared, isn't it? That's 5 over 4 squared, so that's good. Now this is not like this, but a second substitution will get me it very quickly. U equals t plus 3/4. du therefore just equals dt because it's a linear substitution. That's fine. That just replaces in there. That becomes a u. And like I said, I can write that as 5 over 4 squared. And now I've perfectly got something of this form. So a is 5 over 4, 1 over 2 times 5 over 4, and then 5 over 4 here, 5 over 4 here, and then plus u, because I've got this in terms of u now. And we get all of this. Of course, this, so that's 10 over 4 which 1 over is 4 over 10 times a half is 2 over 10, which is 1 over 5. So that's perfect. That matches there. And then this here, you want to substitute, remember the plus k, of course, because I've actually integrated. Replace u with t, which is t plus 3/4. There, so that's good. And then simplify that, simplify this, we get this. This is looking good. Replace the t with the original substitution, which is there. Thank God there are no limits in this question, because otherwise I have to do way more work as well. And we get this, or of course I could have just dealt with those at the end. But anyway, we get this. And now there's a couple of things I can do here. Firstly, I'm going to claim that both of these two things are positive in this range. Of course, this one is positive because tan is positive between here, so this is just 2 plus something. And this is positive because when you put in, tan is increasing from here to here. So when you put in the biggest thing, tan of pi of 8 I checked is like 0.4, so this is positive as well. Positive over positive means I don't need this modulus sign, so I'll just lose it from here. I've also times both of them by 2. It's a fraction, I'm allowed to just times both things by 2. And now I'm going to times the 2 through here to give me this, but I'm going to not times this through 2 here because I like this thing. I'm just going to bring the 2 out the front to give me this. So can you see what I've done now? Just times the 2 through and then brought the 2 out the front like this. Of course, if you were to simplify this, you just times the top row by 2 to get me this, which is fine. But now, of course, I've got log of a product, log of 2 times this. And product rule for logs means like log of AB is log of A plus log of B. So this is log of 2 plus log of this whole fraction here, with the 5th out front, of course, here. Now, half log of 2 is just a different constant, so that just tags on here, and we end up precisely with what they wanted me to get, I think, which is perfect. There was an easier way to do that, just in case you were screaming at the screen. From way back here, you could have just noticed that this factorizes. You know, you can bring out a -1, and it's easier to spot if you do that. It factorizes to make this, I think. I hope I haven't got that wrong, but it factorizes to make this. And then, of course, from here, you can just do partial fractions, right? I've also put this -1 back into there, which just makes the partial fractions. It just means I won't forget this minus, which I probably would have done otherwise. Do the partial fractions, you get this, and then you can put it back in. And you can, of course, integrate this for 2 different logs, which you could then put together because one is being taken away. And I think you get to the answer slightly faster. It's a more elementary way of doing it. But I think everything that I did previously was just good practice. That's nice. But anyway, yeah, so you keep going from there. Good, so now we've got another differential equations question. We've got to first turn this thing into this thing using this substitution or transformation. So okay, we do this. If t squared is e to the x squared, you just times the 2 by the x, which makes this, and then t cubed, the same thing. Now dt by dx is just, of course, e to the x, because differentiating this with respect to x doesn't do anything. But that, of course, equals t, and I'm going to mostly stay in the t worlds for most of this. dc by dt, we can just use this chain rule idea, is dc by dx times dx by dt, and you can just imagine these dx's cancelling, and you just get dc by dt. But we know dx by dt, flip this over, dx by dt is just 1 over t, so I think that equals that. And now, you can't just do a nice easy trick like this to get d2c by dt squared. What you need to do is you need to actually take this and you need to differentiate it. So d2c by dt squared is what happens when you differentiate dc by dt with respect to t. But of course, dc by dt is this, so let's just differentiate this with respect to t. Well, this is a product. So I can leave this one alone here. 1 over t is t to the -1. Differentiate that for minus t to the -2, which is -1 over t squared, and leave this one alone. And then leave this one alone and differentiate this with respect to t. Now, this is probably the most tricky bit, but essentially, just imagine this to be a function of x, right? Imagine it if it was just an x squared. When you differentiate that with respect to t, you get 2x, so the derivative of this, times dx by dt. Right? Because this is some function of x, you just times dx by dt at the end. So derive that, which is this, and then just tag on the dx by dt at the end, as if it was just like x squared goes to 2x with a dx by dt next to it. Okay, so that's fine, we have all that. And now we can just take this, in fact, actually as well, dx by dt is 1 over t again, and 1 over t times 1 over t is 1 over t squared. And now we can take this result, we can take this result, and we can shove it into here. We can also replace t cubed with e to the 3x. I think I've left everything else the same. I have, it looks like it's good. So this cancels, this cancels, we get this. These two go together and we end up with what they asked us to get. Now the good news from here in this question is actually the remaining 12 marks of this are just regular core pure maths A level. So Yeah, all you really had to do to get full marks on this question was learn this bit in FP1 to transform this to this, learn some of that differentiation stuff. And from here, it's just regular A-level, right? You solve the auxiliary equation, which is this. That gives you two real solutions, which is the case where we leave it like this, a to the first, e to the first solution, plus b to the second, x. So that's that. And then we, of course, deal with this. So we just say maybe c equals k e to the 3x. When you've got an exponential, you just use k e to that same number here. That's important. That's the same number there. Differentiate this a couple of times and then substitute it into here to actually solve for k. And we get k as -1. And we tag this -1 e to the 3x on the end of this. So it's particular integral plus complementary function, I guess. And we get our general solution there. And I think and then of course we have to, for c at time t, well this isn't anything to do with t, so we take the x's, we say, okay, well from up here, x equals log t is what I said, and I substitute those into here, and then of course you can do power laws for logs. This 2 bounces up to there, the 4 bounces up to there, the 3 up to there, and then of course e to the log all just cancels, and we just end up with this. And I think that will be all 7 marks earned there. And now we've just got some initial conditions to sub in. So t equals 0, c equals 6, and this. So, okay, well, we can put the first one in very easily. We make this, and then we can differentiate this. Now, of course, that's very easy to differentiate. Now that's just a polynomial. And then we can substitute in -36, and t is 6 again. And we end up with another thing in a and b, which I've just put up there, you can see. Solve this, we get this, I mean, times this by 3. This matches and this matches, so b, whatever, how many b's it is, must be 0. And then you can substitute in to find a times 6, and then sure. And we get this. So that's actually quite a nice simple formula for C now, which is excellent. Maximum concentration of the drug in the patient. So we're looking for dc by dt to be 0. So we can take this if we want to, we can differentiate it, we can set it to be 0, we can solve for t. I factorized out and then set, sure, so 0 or 4. And of course at 0 it's not going to be a maximum concentration, because at 0 you're only just introducing the drug. So at 0 it's not going to be a maximum amount. T is 4 is going to be the maximum. Put it in and you get this. It's worth noting the exam boards required you to write the units, but you can just write them as words. I mean, it literally says there. I don't know why it asks you to do that. I think I may have missed that in previous exams, but I did notice that this time required the units on the end. If you're not convinced that this is definitely a maximum, you could of course derive this as well to get this, and then you can substitute in t as 4, and you're clearly going to get a negative number, which means that it is a maximum at that point. Good, whereas 0 is indeed the minimum, because it's greater than 0. Excellent. I think we only have 2 questions left. We've got a vectors thing first. When I draw vectors with planes, often I like to draw the plane. This looks like a line right now. This is the plane. I'm just looking at it from directly above so that it just looks like a line. And I like to draw things like that just because it helps me see the picture sometimes more clearly. So okay, let's pretend this is the point A, this is the point B, this is the point C down here. We have a line A to B which intersects the plane at P. And we also have a point C, which I'll just pretend is there. Line C to B intersects at Q. And we want to find the area of the quadrilateral, APQC, this one here. Now there's lots of things you could do here. I probably haven't done the most efficient method, but I did like my method. I think it's very instructive, so I decided to keep it. This line here is clearly just going to be pick a point, A or B, it doesn't matter which, and then just say plus lambda how much you need to get from the point you picked to the other one. You can actually be less particular about that, but anyway, 7 minus 5, 0. So that's L1. And then we can write x equals 3 plus 7 lambda, y equals 4 minus 5 lambda, z just equals 5. And we can substitute those results into here to find the intersection with the plane. And we'll get lambda as a quarter when we do that, which means to find the actual intersection, we can just shove lambda as a quarter into there, and we get this point here. 3 plus 7 over 4, 4 minus 5 over 4, and so on. And we get this here as decimals. Okay, now I can do exactly the same thing for Q. So find the line equation L2, which is going to be, we can just pick the point, I think I just picked the point C, and this is how much do I need to get from C to here. Well, that's going to be plus 6, minus 8, minus 14, plus 14 from here to here. Okay, do exactly the same thing, find your x, find your y, find your z, put it into there, solve for lambda, or solve for mu, sorry, I've called this one, doesn't really matter. Put mu into there, and we end up, that's a bit easier, the numbers end up being nicer, don't they? And we end up with this as our q. Now my plan here is to say, well, okay, again, that's a and that's c. My plan here is to find the vector a to p and the vector a to c. Now a to p is just how much you need to get from here to here, which is clearly 1.75 minus 1.250. So that's a to p. And a to c, very similar, is going to be 1 plus 3 minus 14. And what I can do is, if I cross product together a to p and a to c, and then find the magnitude of that resultant vector, I'll find the area of the parallelogram made by AP and AC. And if I just halve that, I'll find the triangle APC. Right? So maybe listen to that again if you need to. When you do this vector crossed with this vector and find the magnitude of the resultant vector, because this of course makes you a new vector, that magnitude, that scalar quantity, is the area of the parallelogram you'd make by just continuing AP and AC out like this. And if I halve a parallelogram, of course, I get a triangle. So I can find the area of triangle APC by doing exactly this. Of course, my plan then is to find the area of PQC in exactly the same way, basically, just with these vectors, and then add the results together. So I think I can do this. I'll get out this familiar cross product matrix that you've probably seen. I'll find the determinant by doing I of this, j of this. That's a minus there before you do the j, and then k of this. Of course, I'll trust that you guys can follow my numbers there. I hope I haven't made any mistypes there, but eventually I got this. And then, of course, to find the magnitude of this vector, this ijk vector here, I can just do this squared plus this squared plus this squared square rooted, times it by a half at the end, and I end up with this figure here. That's the area of the triangle APC. So I'll just jot that down, and now I'll find the vector p to q, or q to p, it doesn't really matter. So that's going to be 2.25, 0.25 minus 7, and then c to q, or q to c, again, it doesn't really matter. This gets you this, and then you can again cross together this and this, which will find the parallelogram, if you find the magnitude of that vector, and then halve it down for the triangle. So it's exactly the same idea. The direction you go here doesn't really make a difference, because you'll just end up with some minuses that just get squared out anyway when you get to this stage here, and you end up with this thing here. I just copied and pasted a lot of this, of course. We get this, we add it to this, and we get the area they gave. There are probably lots of other ways you could have done that. I thought that was a nice instructive way of doing it. The mark scheme found the area ABC, again by just crossing those two together and halving, and then took away the triangle BCQ, which I quite liked as well. But yeah, there were probably lots of other ways you could have done that as well. Good, so the point D has coordinates this. We can actually basically forget the picture at this point. A to B, I think we already wrote down is this, just this to this. A to C, from here to here, is this. And A to D, from here to here, imagine K was 7, 3 to 7 would be 4, so it's just K minus 3 would be what you have to do there. And then, of course, as 4 to 4 is 0, and then minus 6. And the area of a parallelepiped is going to be AD dot with the cross product of the other two, a bit like this. So AB cross AC, and then dot it with the third one. It actually doesn't matter which order you do these. You have to do the cross product first, but it doesn't matter which order you put these three in. You can, of course, also just do scalar triple product if you're comfortable doing that. I just prefer doing like this because this is what I was taught. You can do the magnitude there because, of course, if you've got a negative number, you would just swap it out to be positive. That is going to be irrelevant in a second. Of course, we cross together AB and AC, which gives us, just cross it over here, transpose those, of course, do the determinant, and so on. We get this. So we put that result in here, and then we dot product these. And now the obvious thing to say is it's just going to make this, the middle term goes away, by the way. But of course, because of the magnitude signs here, if this whole thing was minus 226, that would also work because we just say that's equal to 226. So this whole thing, this whole dot product could also be equal to minus 226, and that would also be valid. And that's where the possible values come from. You solve each of these and you get your two possible values. So just a sting there, but they did give you a good hint by giving you this grammar here. Anyway, very last question now. We have hyperbola. As soon as I read this, I go to the formula book and look at my hyperbola cheat sheet, which will be very useful. So we're clearly set up with A is 4 and B is 3. Looking at this, that's good. We can draw it if we want to. Hyperbolas look a bit like this. we have, okay, let's just read this very carefully. We have a general point, which I'm just going to put here, doesn't really matter. General point there. We have a line L1 meeting the x-axis point A. So L1 is tangent at this point. So just draw a line tangent to that, meets it at A. Good. Line L2 is tangent at the point 4, 0. Now, at 4, 0, that's just going to be this point here, isn't it? So tangent to that is just straight upwards, and that's at 4. And then those two things meet at the point B, and the midpoint of AB, so A is the point on the axis, to B, the midpoint of AB is M, and we're being asked to show something about M. There is a lot to do here, as you can see. So let's zoom into the picture a bit. I don't need any of this, obviously, so let's zoom into the picture a bit. And we've got a few things to do. The first thing I decided to do was, of course, differentiate this. So 2 times this is this, drop the power down, minus 2/9 y dy by dx, and then 1 differential to 0. Rearrange that, you get this. And what we can do is, of course, to find the gradient of this line here, we can put this coordinate into there. So that gradient is this. And now we can use y minus y1 equals mx minus x1, I believe, on this point P here. And we'll find the equation of the line. We can multiply this out a little bit. I think I multiplied everything by shine as well here. I did, and by 4 as well, it seems, just to get rid of the fractions entirely. So that's cool. And now actually, I think I can use a thing from the formula book here. Adds 12 sine squared to both sides, and now from the formula book this I believe is equal to 1, so that's very helpful, and this becomes a not too complicated equation of this line, so that's useful. Now of course this line hits the x-axis at the point A, 0, so we can shove in A as our x and 0 as our y. Of course that makes all of this go away, and we end up finding that A is 4 over cos theta, which is useful. We can also put in the x coordinate of 4 into this line to find when B happens. So it hits the vertical line when x equals 4. So put x equals 4 into here, we get this, and we can find y is this. So B has coordinate 4, this here. And what I'm going to do, I don't need any of this bit over here anymore. I'm trying to find M. I know that A is here, so I can draw this picture much bigger like this. So and I was super zoomed in just to this bit here. All I'm interested in is this point, which is here, M, which I don't know yet, and B, which we just said was 4, all of this. And now M is the midpoint, remember. Now to find the midpoint, you just average the x and the y coordinates separately. So we do this plus this divided by 2 is the average of the x coordinates, which will be, of course, this, and the average of the y coordinates is this plus this over 2. 0 plus this is just that, so we just divide that by 2 and we get this. So that's our coordinate for M. And now, okay, that means that if you're on M, you can be anywhere such that x equals this and y equals this, of course, just depending on what you chose theta to be when you were choosing this original point. So this is our x, this is our y, and all I need to show that this is the Cartesian equation is to show that y squared equals all of this. There are much sort of what I'm going to do is the brain dead way of doing it, because I think that's probably what most people should be trying to do in the exam. There will be much more elegant ways of showing this, but what I'm going to do is I'm literally just going to find y squared. I'm going to find all of this in terms of x here, and then I'm just going to show that those two things are the same with a bit of manipulation. So there are much more elegant ways of doing this, but okay, just square y. Oh, first thing I'll say actually is dealing with this P and Q thing. Now the Cosh graph looks like this. Its smallest it can possibly be is 1, and the largest is of course infinity. Now if Cosh x is infinity, you get 2 plus 2 over, essentially 2 plus 0. So the smallest x can be is 2. And the largest x can be, if Cosh is 1, is 2 plus 2 over 1, which is 4. So x looks like it's trapped between 4 and 2. Which will just earn us this last mark here. And now I'm going to do what I said I was going to do, which is square out y. Of course, this is going to be this times itself, so it's this times another copy, times this, cross terms, and then these last two terms, you get eventually this. If you do that, now that doesn't look very helpful. I'll deal with that a bit later, just because I didn't want to deal with it straight away. Let's try and form this thing here. So 4 minus x is this, which of course I can simplify. And then times that by 9, just times those by 9 to get this, and then divide by 4x. So 4x is just 8 and 8 here, so divide that whole thing by this with just some 8s. And now my aim is to show that this thing here, y squared, is equal to this thing here. Okay, so how do I do that? Well, of course, there's some tidying up to do here. So this can be 18 cosh over cosh minus this, which just gets you this. And this can be 8 cosh over cosh, and then you add this. These two coshes cancel, you get this. That's already looking a bit better. You can divide everything here by 2 to get this. That's looking quite good. There doesn't seem to be too much more I can do with that very easily straight away. So let's look back over here. Now, of course, I can combine all these things together, times this middle one by 2, and then put them all together. And now when you factorize out the 9, you get a good hint. This is a good hint. Like, that is a factorizable quadratic in terms of cosh. But how is that helpful? Well, the problem is that this only has coshes in it, right? I'm trying to show this is the same as this. Now, I'm okay with being coshes in here because there are coshes in here, but the sinh I'm not okay with. Get out the formula book, and notice you can write sinh squared as cosh squared minus 1. So I can replace that with cosh squared minus 1, and now it all comes together because that factorizes, as I said, into cosh minus 1 all squared, I believe. This is a difference of two squares. This is cosh minus 1, cosh plus 1. And of course, this can cancel with this. And we get this, which I believe, if I factorize out of 9 and a 4, is equal to that. And therefore, y squared is equal to 9 4 minus x over 4x. Good. So not a very elegant or delicate way of doing that, but probably the method that you should be aiming to do because it's the most brain-dead thing to do. The very last bit of the paper here, S is the focus of H. So okay, we again get out the cheat sheet, look at the focus. Okay, so it's AE, where E can be defined here. So B is 3, A is 4. Substitute those in to find E. We get E is 5/4. We don't care about the minus because it's on the positive x-axis. So of course, we don't care about the minus because E is greater than 1. And then when we substitute it into the foci, we don't care about this minus option here. We'll just do 4 times this, which is of course 5, and we'll get that the foci is at 5. And now, thankfully, just always look at the number of marks. This is 3 marks. You've almost certainly got 1 mark at least for finding E. You've probably got another mark for finding that this is now at 5, 0. You've got minimum 2 marks. You can only possibly be looking for 1 more mark here. So please don't do some Pythagoras with that general term for m that we found earlier to 5. All you need to say here is that the distance from the foci to this point here is 1. M is outside of the curve and is thus further away from this than 4 is, but 4 is already 1 away, so therefore M is further than 1 away. You just need to blag that. So please just read how many marks the question is worth. Don't dive headfirst into some horrific maths when you're only looking for 1 more mark in the entire paper. Just read the marks, and in A-level maths, there's lots of blagging that's completely acceptable to do, and that will be that. Good, I think that's the entire paper. Thank you so much for watching, and I'll see you next time.